Now we are moving into exception handling. So far, we have seen that programs can produce errors when something unexpected happens, such as missing files or invalid input. Exception handling allows us to manage these situations in a controlled way instead of letting the program crash. It helps us write more reliable and user-friendly programs by anticipating and handling errors properly. Exception handling is the process of responding to errors that occur during program execution. Instead of allowing a program to crash, we can detect and handle these exceptions in a controlled way. Common examples include zero division error, which occurs when dividing by zero, and value error, which occurs when an invalid value is used. Understanding how to handle these situations is essential for writing reliable and robust programs. This is a simple example of a zero division error. We define A as 10 and B as 0, then attempt to divide A by B. Since division by 0 is undefined, Python raises an error and the program terminates. This is a common type of runtime error and highlights the importance of exception handling. Rather than allowing the program to crash, we can handle this situation using exception handling. This example demonstrates a value error. The program asks the user to enter an integer, but instead the user enters a string, apple. Since Python cannot convert this input into an integer using int function, it raises a value error. This is another common runtime error that occurs when the input does not match the expected type. Using exception handling, we can catch this error and prompt the user again or handle it more gracefully. This slide shows the general structure of a try statement. The try block contains the code that may cause an error. The except block handles the error if one occurs. The else block runs only if no exception occurs in the try block. The finally block runs no matter what, whether an exception occurs or not. Not all parts are required, but this structure gives you flexibility in how you handle errors in your programs. This example shows how all parts of the try statement work together. In the try block, the program asks the user for two integers and performs division. If any error occurs, such as invalid input or division by 0, the except block runs and prints an error message. If no error occurs, the else block executes, indicating that everything worked correctly. Finally, the finally block runs no matter what, printing a message before the program ends. This structure allows you to handle errors while still controlling the flow of your program. This slide shows different possible outputs of the program. In the first case, division by 0 occurs, so the except block runs and prints error, followed by the finally block. In the second case, valid inputs are provided, so the division is successful. The else block runs, and then the finally block executes. In the third case, invalid input is entered, which causes a value error, so the except block runs again. In all cases, the finally block executes, demonstrating that it always runs regardless of what happens. When working with exceptions, you can use multiple except blocks to handle different types of errors separately. Each except block is designed to catch a specific exception type. Python checks them in order and executes the first matching block. For example, a value error is handled differently from a zero division error, allowing you to respond appropriately to each situation. This approach makes your code more precise, since each type of error can be handled with its own logic. If a general except block is used, it should come last because it will catch any remaining exceptions. This example demonstrates how multiple exceptions are handled. In the try block, the program reads two integers and performs division. If a non-integer value is entered, a value error occurs and a specific message is displayed. If the second number is 0, a zero division error occurs and a different message is shown. If no error occurs, the else block runs, and the finally block executes in all cases. Handling exceptions in this way allows the program to respond to different errors more clearly and appropriately. This slide shows how the program behaves with multiple except blocks under different inputs. In the first case, the second number is 0, so a zero division error occurs, and the corresponding message is displayed. In the second case, a non-integer value is entered, which causes a value error, and a different message is shown. In the third case, both inputs are valid, so the calculation is performed, the else block runs, and the result is displayed. In all cases, the finally block executes, printing goodbye at the end. This example shows how to manually raise an exception in Python. Inside the function, we check if the second number is 0. If it is, we use the raise keyword to generate an exception with a custom message. This allows you to enforce rules in your program and stop execution when an invalid condition occurs. When the function is called with 10 and 0, the exception is raised, and Python displays the error message along with the traceback. Raising exceptions is useful when you want to signal that something has gone wrong and ensure that the issue is handled appropriately. This example shows how a raised exception can be handled using a try and except block. Inside the function, we explicitly raise an exception when the second number is 0. When the function is called, the exception is triggered, but instead of crashing the program, it is caught by the except block. As a result, the program prints, "I am handling the error," and continues execution. This demonstrates how raising exceptions and handling them together allows you to control program behavior when errors occur. There are two main approaches to handling errors. The first option is to handle the error directly using try and except. This allows your program to catch the error and respond to it immediately. The second option is to raise an exception. In this case, the error is passed to another part of the program, which is then responsible for handling it. These two approaches give you flexibility in how you design your programs and manage errors. Assertions, or assert statements, are built into Python and are mainly used for debugging. They allow you to test whether a condition is true while the program is running. If the condition is false, Python raises an assertion error, optionally with a message. Assertions are commonly used during development to check assumptions in your code. Unlike try, except, and raise, which are used for handling runtime errors, assertions are primarily used for testing and debugging purposes. This example shows how an assert statement works in practice. We assign n a value of -10 and then assert that n is greater than or equal to 0. Since this condition is false, Python raises an assertion error. This indicates that an assumption in the code has been violated. This example may not seem very useful at first. However, in larger programs with many lines of code, a variable may be modified or used in many places. In such cases, assertions help you verify that the variable still has the expected value. Assertions like this are useful for catching logical errors during development. This example shows how to include a message in an assert statement. We assert that n is greater than or equal to 0, and if the condition is false, Python raises an assertion error with a custom message provided. In this case, the message clearly explains the issue, that n should not be a negative number. This makes it easier to identify what went wrong during debugging. Using assertion messages is a good practice, especially in larger programs, because it provides more context when an error occurs. In the next lecture, we will move on to slicing. Slicing allows you to access and manipulate portions of sequences, such as strings, lists, and tuples. It is a powerful and commonly used feature that makes working with data more flexible and efficient. We will explore how to use slicing to extract, modify, and analyze data in your programs.
Thank you for your attention today. This presentation was prepared by
Junbi.
with assistance from AI Technologies. I truly appreciate your engagement. See you in our next class.